for Sam and Addie and Ryan. Slackers.
All those out.
I'm telling you. Okay, so let's think about the things. Let's talk about the things we know. If we're throwing something at an angle, right? If we're throwing something at an angle, then we have to take that velocity and turn it into its separate dimensions, right? Its components. All right? So the x component becomes v cosine theta, and the y component becomes v sine theta. All right? So we know that. What do we also know? At the max up here, when we're up here at the max height, this is our max height. What do we know about the velocity at our max height? Oh, be very careful.
In the direction.
Yes. V sub y is equal to 0. V sub x, however, is what? Constant. Good. It is still v cosine theta. Okay? The horizontal, it's not going to be a, no, you can't have it be 0 both ways. Otherwise, it's just sitting there in space. It's not moving. That doesn't happen, does it? It doesn't just go whoop and sit there. Okay? So, what else do we know? So this is going to be our v sub x component. V sub y component is non-existent. And what do we know about gravity? Going downward. So our acceleration vector is only in the y direction, isn't it? So a sub y is 9.81. It's really negative 9.81 meters per second squared at that height. Okay? And it is perpendicular to the path. It is always perpendicular to the path, isn't it? So this acceleration at the top right here. Now, we can't say it's perpendicular necessarily to the path in every position along the path because it's not, the velocity is what's perpendicular. The resultant vector of the velocity is what is perpendicular at every point in this pathway that we've got drawn, because the path we've got drawn is the position graph, isn't it? So that really is the position graph of this object. So what we know is if we needed to find the, say, the velocity here is now this way. Velocity here is now this way, isn't it? Velocity at the top is now all in this direction. Now, as it turns, remember velocity is now this direction. So we've got big V. This is not V sub x and V sub y. This is the resultant V. But the acceleration is everywhere, because it's just due to gravity, is still straight down everywhere. All right? That is a result of the resultant of the x and y components of the acceleration. Well, there isn't any acceleration in the x direction since it's just gravity, so we consider all of it just going down. Okay? Now, x and y components, if you remember, are mostly considered separately, aren't they? So in the x direction, we know this. We know a sub x is equal to 0, and v sub x is going to be equal to v cosine theta, and the horizontal distance covered, remember this delta x is going to be equal to what? V initial in the x direction t plus 1/2 a sub x t squared. But what do we know about a sub x? 0, so that part of the equation goes away. So really what we know is that the change in distance is just V initial times t here. Okay? And if we wanted to, we could actually plug this in and say delta x is equal to, because we know what V initial is, it's going to be V cosine theta times t. Now, y direction. What do we know about the y? A sub y. Yeah, it's negative g, which of course is negative 9.81 meters per second squared. What do we know about v sub y of t? What is it going to be? It's not just going to be v sine, is it? Because gravity's acting on it, isn't it? It's going to be v initial plus at, isn't it? So it's going to start out as v initial plus a times t. That's v final, right? So at any point, this is going to be v sine theta minus gt. Right? Okay. Now what about the height? Y of t is going to be what? Y initial, v initial in the y direction times t plus 1/2 what? At squared. So what goes away? What's y initial? Well, whatever y initial is, right? What is v initial in the y direction? So basically you can say delta y, because we can move this over and call it delta y. This is going to be v sine theta, isn't it? Times t minus, really minus, right? Because what's a? 1/2 g t squared. Okay. So vector notation. Let's take this into vector notation. What do we know about the acceleration vector? What is the acceleration vector component going to be in the x direction? 0. So it is going to be 0 I hat minus g j hat. There's our vector notation for that. Our vector for v, let's combine the two things we found. What did we find the x component was? It was v cosine theta, right? Times I hat plus, we just found this, didn't we? V sine theta times t. Oops, sorry. This is times t, isn't it? Did I leave a t out? I did, didn't I? Times t in the I hat direction plus v sine theta t minus gt. That is in the j hat direction, isn't it? Oh, nope. Look at me, guys. It's been a long day for me too. I put a t in. I didn't put a t in where I needed to. I put a t in where I didn't need to. In other words, do you see what I just did? I took this chunk and hang on. Nope. It's this chunk and this chunk, isn't it? Here. Miss Duffy's tired. It's been a long week. So if we look at this, it's v cosine theta. I was right the first time. It's what? V cosine theta. V cosine theta in the I hat direction. Y'all stop me before I do something wrong again. V sine theta minus gt in the j hat direction. Golly. Because it's not changing in the x direction, is it? So it can't have a t. Now, position vector. This is where we're now going to take what we took from the position vector here and here. Aren't we? There's where the t's come in, correct? So this is going to be what? V cosine theta t I hat plus, what did we get? That big ugly right there. V sine theta t minus 1/2 gt squared in the j hat direction. So now we have vectors for all three of those behaviors. It's a very different look when you're looking at it, all of this stuff from, but it's the same basic equations. We're just making it more complex. So ask yourself, example A, it says, what assumptions are made in order for the formulas above to be valid? Acceleration is what? Negative g, right? And constant. It's not changing. Remember, kinematics only works with a constant acceleration, doesn't it? Or zero acceleration, which is constant also. These also only work when we consider that air resistance is negligible, right? Okay, so no air resistance. Because if there's air resistance, we got to switch from kinematics to Newton, don't we? And look at it from that point, okay? So no air resistance while it's in flight. Now that's not really super realistic, but kinematics is limited, isn't it? It's limited in what we can do with that. Now, most of the time, if we're in a pretty calm environment, etc., and something's moving really, really fast, we don't have to worry too much about air resistance. It's just when we get into really thick atmospheres, if we get into fluids, a liquid of some sort, or a heavy gas, that we have to really start worrying about air resistance. Or if the surface area is big. So if you're shooting an arrow, which is skinny and pointed, and you're just shooting it downrange, do I really have to worry that much about air resistance? No, it's negligible. So in that regard, we wouldn't have to consider it. We could use kinematics. However, if I'm trying to push a box down or a big, heavy something, wide something down range, and I'm trying to push it through, say, oh, I don't know, water, do I have to worry about resistance? Yes, I have to worry about it pushing back. Coffee filter dropped from the balcony to the floor. Guess what? Coffee filter's light enough and it's got enough surface area that it will. Air resistance is a thing. It really is. Because remember, if I drop a bowling ball and a coffee filter in a vacuum, they fall at the same rate, don't they? There is no air resistance because there's no air. That's what it means to be in a vacuum. They fall at the same rate and hit the ground at the same time. However, if I take them out there to the cafeteria before I get fired for breaking the floor, drop a bowling ball and a coffee filter, which one's going to hit the floor first? Bowling ball. I'll be fired before the coffee filter hits the floor. So, but you see what I'm saying. All right, so a projectile is launched from ground level. Let's look at this example. With an initial velocity v at an angle theta above the horizontal. Okay, it says calculate the maximum height reached by the projectile. So we want to do the maximum height. What do we know? First thing we know is we've got v naught, don't we? So we've got v naught. Oh, actually, we don't have v naught. We have a v. Excuse me. Let's just call this what they call it in the problem, right? Which is v. So we got to break v down, don't we? So max height here, let's call this h. Max height is h. What do we know at this max height that we can help us? We know acceleration in the x direction is 0. We know acceleration in the y direction is negative g. We know velocity in the y direction is 0. Velocity in the x direction is v cosine theta, isn't it? We don't know time though, do we? We don't know nothing. So we got to figure it out. So let's do this. What do we know? Let's look at our kinematics equations. We know that v what? V final is equal to v initial plus AT, correct? Yes? Is that going to help me? Yeah. Maybe. Well, it depends on which axis we're doing. Look, we got two equations and we got one unknown, which is we need time, don't we? To plug in to get the distance formula. So we got to do something to get time. We do know enough here to use this, don't we? V final, if we're talking about in the y-axis, in the y direction, let's do y direction stuff, right? So the y direction, we know V final is 0, correct? V initial in the y direction is going to be what? V sine theta minus GT. Can we solve for T? I hope so. Subtract V sine theta to the other side and divide. Now, before you get all hung up in that, is there an easier way to do this? Is there an equation that can help us bypass time and just get the height? Look at the equation sheet. Ah, so this is ugly, isn't it? You're gonna have to plug that in and square it. It's gonna get ugly. So would we prefer to maybe not do that? Cross it out and say, bleh. But that's probably where you would start. That's the reason why I did it that way, is because a lot of times that's where you're going to start, right? And it's going to get ugly fast and you're going to go, yuck. So it means sometimes stop and take a second look. So what do we know? V final squared equals V initial squared plus 2a delta y in this case, right? So V final is 0. V initial is V sine theta, correct? We'll square that, plus... So minus 2g delta y. I did the minus thing. Plugged in what I know. So now can we directly solve for delta y? The answer to that is so 0 equals v squared sine squared theta minus 2g delta y. Going to take this over, we get negative v squared sine squared. I'm going to chalk it up to you guys being very tired today. And then what are we going to do here? Divide by 2g, negative 2g. So delta y is going to be, it's going to go positive v squared sine squared theta over 2g. So there's part A. That would be the maximum height it will get to. So now what does it say? Find the time the projectile is in the air. Ooh, okay. Now we can use our V final one, can't we? Wasn't that going to give us time? Okay, so let's do that one. Part B, we're still in the Y direction, aren't we? V final equals V initial plus AT. What is V final? If we're at the top, 0. V initial was V sine theta minus GT. So T is going to be what? V sine theta over G, but here's the problem. It says find the time the projectile is in the air. Is that what we have found? This is what we found, isn't it? So how can I find it all the way to here? multiply by 2. So total time, so t air is going to be twice t, which is going to be 2v sine theta over g. Right as rain, right? C. What does C ask? Find the horizontal range of the projectile. Woohoo! So now we've got to find delta x, don't we? This shouldn't be too bad. What is delta x? B initial in the x direction times t plus 1/2 a in the x direction t squared. And what do we know about that last part? Goes to 0. So this really is not that bad, is it? What is v initial in the x direction? V cosine theta. Yep. And what is t? The total time. We just found it, didn't we? 2v sine theta over g. So this becomes 2v squared cosine theta sine theta over g. And now I need you to remember something from trig. What did we remember that 2 cosine theta sine theta was equal to? Just so you know. It's equal to sine of 2 theta, isn't it? So we're going to replace, just so you can see what I'm doing, I'm going to replace this and this with this instead. So what do we figure out it is? Delta x is v squared sine of 2 theta, twice the angle, divided by g. So at what angle is this? The last part of the question says at what angle will allow it to reach its maximum horizontal range? Here's how we figure that out. This thing is going to be maximized when this is a max. And here's how you think this through. When is sine at a maximum? 90 degrees, right? Sine is at a max up here. So what we need to figure out is we need to know sine 2 theta is maximum when theta equals what? Well, set sine 2 theta equal to, well, 2 theta equal to 90 degrees, right? Sorry, leave the sign off. 2 theta equals 90 degrees, so what is theta equal to? 45 degrees. Does that not make sense? It's going to go the furthest down range when it's exactly 45 degrees. Guys, when you look at something like this, what you're going to see is this. If you were to look at a problem like this and look at it downrange, at 30 degrees, it's going to go like this and come down. This is 30 degrees. At 60 degrees, it's going to go up higher, but it's still going to come back down in the exact same spot. So it's 60 degrees, but it's, yeah. So it'll just stay in the air longer. But 45 degrees is going to go not as high, but further down range. Okay? So that's kind of what it looks like. But 30 and 60 will go the same. They'll end up in the same place. It's just going to take the 60-degree one longer to get there because it stays in the air longer. All right? Okay. So projectile motion. Now the thing about projectile motion is we've got to remember that we've got to break stuff into horizontal and vertical components. And we've got to work the horizontal. Usually, if you remember, we work the horizontal stuff to get time or the vertical stuff to get time, and then we plug that into the other problem, don't we? So we're working them kind of simultaneously. So a ball rolls off a table that's a height h above the ground. It travels a distance x horizontal while it's in the air. How long is the ball in the air? So now we got to figure all this out. And we got to look at it from that standpoint. We don't even have any numbers here, do we? And I'm not going to give you any numbers until the next example. So part A, how long is the ball in the air? That's an angry red. I'm going to go to blue. It feels more friendly. Or maybe I need to be angry with y'all. Keep you awake. So we know a delta x, don't we? How long's the ball in the air? What speed does the ball roll off the table? So we know it's just going to be going this direction, don't we? So let's start with the y direction. I usually start with the y direction, see what I have, and then look at the x direction. So in the y direction, what's the initial velocity in the y direction? Zero. It's rolling off the table sideways, isn't it? So it's 0. All right, do we know the acceleration in the y direction? Negative g. Do we know delta y? How far did it fall? Negative h, right? Because we're calling this what, 0? It is a height h above the ground, so we're considering that 0, aren't we? All right, so we've got that at negative h, and we don't know time, do we? But we could find it, couldn't we? What does it look like we can use? Delta y equals what? The initial in the y direction, t plus 1/2 a t squared. So this is negative h. This is 0, isn't it? So we got 1/2 negative g t squared. And see, here's the thing. If you were to have done this wrong and put an h instead of negative h, when you went to take the square root, you'd be taking the square root of a negative, wouldn't you? That would be a clear sign that you probably should put a negative in front of that h. Look at it again and get rid of the negative. So you can catch those mistakes if you're aware. So if we solve this, we know the negatives are going to go away, don't we? So we get 2h over what? And then we're going to take the square root. So we get t equals the square root of 2h over g. All right, so that's a. Now, we used a to find the y direction to find time, which means we're going to use what? X direction probably to find the speed with which it rolls off the table. Because we want to know v initial in the x direction, don't we? That's what we don't know. So what else do we know that's in the x direction? We know delta x, don't we? Look at your picture. What is delta x? X. We know t. Square root of 2h over g. And what about a sub x? Yep, it's 0. So delta x, the initial in the x direction times t plus 1/2 a t squared. But what can we mark out here? This goes to 0, doesn't it? And guys, on the test, you either need to indicate here that it's 0 or mark it off here and show that it is 0, okay? So all we have to do to figure out, we know this is x, isn't it? Positive. We don't know v initial in the x direction, but we do know t is root 2h over g. So now all we have to do is what? Flip it over. So v initial in the x direction is going to be x times square root of g over 2h. If you're dividing by a fraction, you're just multiplying by its reciprocal. Still stays a square root, doesn't it? All right. And a lot of times on this test, you'll be working with just variables. You'll notice that a lot. They like to make you work with just variables quite a bit. They'll say derive a formula for in terms of constants and the following variables. And that's what you have to do. So D, in a typical fit of rage, Philip throws his physics book off a cliff. You've been there, haven't you? At an angle of 30 degrees above the horizontal, at a velocity of 10 meters per second. It lands 100 meters from the base of the cliff. So now we actually know some actual numbers, don't we? Don't forget, though, to write the formulas down. If you're working free responses, a lot of times you get points for the formulas and for the things that you make go zero, that you recognize go to zero. So how long the textbook is in the air, we got to look at what we know. So let's just start listing the things we know. We know v initial in the x direction, don't we? How can we find that? We know 10 is this way, so we need to break it down into its components, don't we? So v initial in the x direction is going to be 10 cosine 30. We're going to know v initial in the y direction because that's going to be 10 sine 30. So let's go ahead and find those. I know this is 5 meters per second. Or is it about 8.7, 8 point what? 8.66 meters per second. Okay, cool. We also know acceleration in the x direction is 0, and acceleration in the y direction is negative 9.81 meters per second squared. We also know delta x, don't we, is 100 meters. We do not know delta y, though, do we? And we don't know time. But that's what it's in common with both of them. That's why we always have to solve for time first, because it's the only thing that's on both sides of this. So which side do we have enough material on to actually solve for something? X. So we know v initial ax, we need to find delta xt, so we're going to use delta x equals v initial in the x direction t plus 1/2 a in the x direction t squared. We're going to go ahead and mark that out and say it's 0 because we indicated it was 0 up above, right? And then we're going to plug in. We know this is 100. This is 8.66 times t. So t is what? Yep. 11.5 seconds. Okay. So that's part A. Now let's look at part B. How high is the cliff? X direction or Y direction? Y. This time we're doing the Y direction, right? So that's for part A. And really, if I were doing this on a test, honest to goodness, I would do this. I would put a line between and I would now go to part B over here. Because, you know, part A. So for part B, we're going to do delta Y equals v initial in the Y direction t plus 1/2 a sub yt squared. We know that that is not 0 this time, is it? So we got to plug in. This is what, 5 times 11.5 plus 1/2 negative 9.81 times 11.5 squared. What'd you get? Five what? 591.2? Okay, 591. Because 3 sig figs. So 591 meters. All right, now, part C. With what velocity, magnitude, and direction does the textbook strike the ground? So notice the textbook's not coming straight in, is it? It's coming in. This is V final. So what we have to do is find the components and combine them back together, don't we? So this is where it gets a little more difficult. We've got to find V final in the Y direction and V final in the X direction. But V final in the X direction should be really, really easy, shouldn't it? Because what do we know about the velocity in the X direction? Constant. So V final in the X direction is what? 8.66. Since it is constant, and I would probably write that down out to the side because I want them to understand that I know that it's constant. Now we got to find V final in the Y direction. That is V initial in the Y direction plus A T. Correct? So plug in. V initial in the X direction was 5, wasn't it? Didn't we say it was 5? Minus 9.81 times 11.5 seconds. It's negative what? Negative 107? Negative 108 meters per second. Makes sense, doesn't it? Should be negative. It's pointing down. Always double check that. Look at your picture that you drew and ask yourself, if you got a positive here, you'd have to ask yourself, but the V sub Y final is downward. Something went wrong. Okay, so we've got this. Now we got to put it together, don't we? So V final. Pythagorean, isn't it? V final in the X squared plus V final in the Y squared. It's all vector math. So what'd you get? Huh? About 108? Yeah. Okay. Yeah, if it's a whole lot in what? This direction and not a whole lot in that direction, is it? Okay, but what about the direction though? How do we find the direction? Inverse tangent. Inverse tangent of V final in the Y divided by V final in the X. So let's take the inverse tangent of, what was it, negative 108 divided by 8.66. Make sure you're in degrees. Should get, it's fourth quadrant, isn't it? Is it? Yeah. Positive, negative. Fourth quadrant, so it should be a negative angle, shouldn't it? 80 what? 85.4, yep. Now, really the way I would write this is I would write it as 85.4 degrees below the x-axis instead of writing it as negative 85.4 degrees. Okay? So far, so good? Coming back to you. This next one is a variation on a problem that we see over and over and over and over and over again. This is a problem that has been on the doggone AP test as a free response a couple of times in different forms. I've seen it as a castle and a castle wall. This is the Disney castle, obviously, but I have seen this AP question. I could probably dig it up for you. A cannonball is shot at a castle 100 meters at an angle 30 degrees above the horizontal. It hits the castle wall at a height of 20 meters above the ground. What was the launch speed of the cannonball? So again, start with listing what you know in the x direction and the y direction. Do that now. Do you know why this problem is so famous? What do you notice you have to solve for first? Yeah, but what they ask for first? Launch speed. This is famous because it was such a stupid question at the time. I like to include it just because sometimes if you can't get the first part of the question, sometimes you can go and get the second part of the question, and it's easier to do the second part first than it is the first part, right? This was a tough question because you're missing so many things, aren't you? We don't know what time is, and we don't know what initial velocity is, do we? But they've given us x and y, haven't they? So we're going to do this the long way, and we're actually going to solve the ugly way to do this and not do time first. We're going to actually do time second. Because you can, but it's easier if you do time first. All right, so let's do part A. We're given delta x, aren't we? The initial xt plus 1/2 a sub xt squared, that goes to 0. So this is 100 equals V cosine 30 degrees times T. Okay. And we know delta Y equals V initial in the Y direction T plus 1/2 T squared. Okay, so this is 20. V initial in the Y direction is V sine 30 degrees times T minus 4. Well, we'll wait to do that until the very end. Minus 9.81 divided by 2 times T squared. So what do I need to do here? I need to solve for T in one of them and plug it into the other to find the V, don't I? Do you see I have a vehicle for that now? Yeah. V cosine 30, V cosine 30. And now I've got T in terms of that. So now it gets ugly. 20 equals V sine 30 degrees times 100 over V cosine of 30 degrees. So that's not too bad, is it? That's gonna even out nicely, correct? It's just gonna become tangent. And the V goes away. Yay! Minus 9.81 over 2 times what? 100 over V cosine of 30 degrees squared. All right, well, let's slog through the math. 20 equals 100 times the tangent of 30 minus, what is 9.81? Is that minus 4.905? Times 100 squared divided by V squared cosine squared of 30 degrees. Okie dokie then. Would like to make this a proportion at some point, wouldn't you? We can now, if you'd like. We're just going to subtract, flip over, and divide. You want me to walk you through it step by step? This is the part y'all got to get better at. So how would you normally solve this? Think about it. I got to get V by itself, don't I? So do I have anything on the side with V that doesn't have a V in it? Yeah, 100 tangent 30, right? So I can subtract that over. 20 minus 100 tangent 30 degrees equals negative whatever this is. 100 squared times 4.905. I think it's going to end up being like 49.05. Was that right? 49.05? No, I might have. Because 100 squared that's 4 zeros. So that'd be 4 decimal places, wouldn't it? Okay, it's going to be 140. Let me see. Hang on. 100 squared times 4.905. 49,050. Oh, man, is it a day. 49,050? Divided by V squared cosine squared of 30 degrees. Okay. So now I'm going to take and move this over here and take that and move it over there. I'm just going to swap across the diagonal. And then I'm going to solve. So now I have v squared cosine. I'm going to leave the cosine squared there. Do I have to take it with me? Nope, I can leave it. So v squared is equal to negative 49050 divided by cosine squared of 30 degrees times 20 minus 100, 10, 30 degrees. Woo! So now we can start calculator jockeying that bad boy. Now, guys, can I give you a hint? Do this first. You've got an inverse button on your calculator. Do this first. Multiply it by this squared. And then use your inverse button to flip it over. And then multiply it by this. Get it? Did you realize you could do that? Be smart on your calculator. So 20 minus 100. Ooh, that would be smart if I were in the right modes. I'll do what I don't know how to do. You know now. All right, now try again. 20 minus 100, 30. Invert that back away. Times cosine. Cosine 30. Squared. Invert it. And multiply by 49250. I got negative 1,733.13 something. Is that what you got? Okay. Do the bottom first. No, do all of it and then invert it. Because you got to invert the entire thing. Okay, so start with me. 20 minus 100. 10, 30. In it. Times cosine of 30, right? Don't square it yet. And then times cosine of 30. Because that would be cosine of 30 squared. You get negative 20 to come through. Now invert it. Hit inverse and hit enter. Now multiply that by 49050. Inverse, no, inverse button right here. That flips something over. And since it's on the bottom, instead of dividing it, you multiply by its inverse. Now, we got to take the, times the negative, right? Times negative 1, because you got to get rid of the negative, correct? That inverse. Here. Oh, we already inverted it. Oh, you got to multiply it by the 49,050. Oh, okay, yeah. And then take the what? You got b squared. So now to get b, what do you do? Root. So second root, second answer, I get 41.6. All right. So the initial velocity is about 41.6. Okay, so there's initial velocity, and that's all our space. Darn them in their hard problems. B, how long is the cannonball in the air? Well, that one's going to be easy, isn't it? Because don't we have now a formula we can use? Look right over here. What do we know? We've got t in terms of it, don't we? So use what you found. We know that t is equal to, and we just found it from the other side, 100 divided by v cosine 30. And we know what v is now, don't we? So just plug in. V is 41.6. So how long did it take? Got what? What'd you get? 2.78? Okay. Alrighty. Ta-da. Now, let's talk about how they would score something like this on the AP exam.
Good afternoon, Austin High School. We had another great day here at Austin High School. I'd like to wish congratulations to our football team on the big win last night against Florence, and also a big win by our JV and varsity volleyball team against Decatur yesterday. Great job by our sports teams. Again, we had a great week here at Austin High School. Everybody please be safe this weekend, and we'll see everybody back here on Monday. Have a good day.
Being able to put down that one equation right there would be worth 1 point. Probably zeroing out right here and saying up here that it's 0 and getting rid of it would be worth a point. All right. And then solving it in terms of t, another point. You'd get a point probably then from starting on this side and plugging in. So at this point you get plugging in your values, you've got another point there. You would also get another point for plugging in your t. That would be a biggie. And of all of those points, you would probably only get 1 point, if at all, for solving then for the actual answer. So notice that the really hard parts of this, which was grinding through all of this stupid algebra crap, is worth 1 point. Then you would have gotten another point for going back to this, got a point, and for plugging in whatever value you found. So even if you get frustrated and can't find one, make something up and put it down here that works with your math, right? Keep slogging through, get a bad answer, and then take that bad answer but indicate that you're putting it there. We call that a follow-through point. You would still get a point for plugging in there, and you'd probably get 1 point for getting the correct answer. So you can see that the really ugly parts of it are still not going to be that bad, are they? I mean, it sucks, but to have to grind through all of that. But also notice that your answer, the thing right here, there's a hard part of the problem and then there's an easier part of the problem. And the easier part of the problem usually feeds off of the harder one, doesn't it? The second part is always going to feed off the first part. And so on as you go down the problem, okay? So don't get frustrated by it. But you can see there's a lot of points sitting in there. But again, you get a point for theoretical and theoretical. And then formula manipulation. You get points for substitution of values and substitution of variables. And then for following through and taking and finding the second part of the equation after that. So, of course, the harder part of the problem is going to be worth more points. Look at the difference here. You've got possibility of 1, 2, 3, 4, 5, 6 points here, but only 3 points here. So there would probably be more parts to this problem, and I think there were in the AP question. I think there were like 4 parts because each question is worth 15 points. And so far, I've only seen, 3, 4, 5, 6, 7, 8, 9. So there would still be 6 points sitting out there. So there would be some other part of it that you didn't know. Okay? So there we go. Are we good? Okay. I think that's it. We only say that you do have homework, which is the projectile motion problems. And we'll go over all the homework next time.